In this video, I'm going to go over the maximum power transfer theorem, which is important for understanding why impedance matching is needed in RF electronics. So to start off with, we have this circuit shown here with a sinusoidally varying voltage source, along with a source impedance CS and a load impedance ZL. So the question behind the maximum power transfer theorem is that suppose we have a fixed source impedance. So that means that the source resistance RS and source reactance XS have already been determined. And now we want to select the values for the load impedance ZL such that the power delivered to the load PL is maximized. In other words, we want to find RL and XL such that the power delivered to this load is as high as possible. So Vs represents the voltage phasor's RMS value. So we can proceed to find the current phasor's RMS value, I. And once we found this current phasor's RMS value, the power delivered to the load can be expressed as the current phasor's RMS value's magnitude squared times the real part of the load, which is the resistance RL. So no real power is actually dissipated in the load reactance XL. So therefore, we only consider the power as being dissipated in the real part, which is the resistance RL. So to find this current phasor's RMS value, I, this equals Vs over the total impedance Z total. And Z total is given by the series combination of the source impedance Zs and the load impedance ZL. So we know that the series combination can be expressed as just adding the real parts together, Rs plus RL, and the imaginary parts together, XS plus XL. Now the quantity squared is going to be equal to the magnitude of the voltage phasor's RMS value squared over the real part squared plus the imaginary part squared. And we know that the power delivered to the load PL is going to be this expression times RL. So this gives us the power delivered to the load. And we thus have an expression for the power delivered to the load in terms of the source and load resistances and reactances. And this is the quantity that we want to maximize with respect to. So we want to maximize this expression, maximize with respect to XL and RL. Because we know that RS and XS are already fixed. So we can see that XL only appears in one location, and that's in the denominator. So to make PL as high as possible, we want to make the denominator as low as possible. So therefore, we want to minimize this term. To minimize this term, since this is under a squaring function, we want to set XL equal to XS. Is equal to negative XS. So these two terms will cancel each other and we get a 0 squared to minimize the denominator. So thus the optimal value to choose for the load reactance is the source reactance negated. So with this choice of the optimal load reactance, the power expression can be simplified to Vs squared times RL over Rs plus RL squared. So now we want to maximize just with respect to RL because we've already found the optimal XL value. So I'm just going to get rid of the star here because it might be confused with the conjugate actually. So let's just call this optimal XL is equal to negative XS. So in this case, we know that one method to find the optimal RL is to take the derivative of this expression with respect to RL and set it equal to 0. So if we take the derivative of this expression, we can pull the Vs squared out because it's just a constant with respect to RL. And we get that we want to take the derivative of this function with respect to RL. So this is the quotient rule that we can use the formula for. So we have that the derivative of RL is just 1 times the denominator. And then we want to subtract. Okay, so we have the numerator, and then we want to take the derivative of the denominator, which gives us 2 times Rs plus RL. And in this derivative of quotient formula, it's all over the square of the denominator. So the squared of a squared will give us a quartic. So now this is our expression for the derivative, which we can simplify by taking out this factor of Rs plus RL. Factoring this out, we get Rs plus RL squared, no squared there, minus 2RL over Rs plus RL to the fourth. And we should also remember that Vs squared factor. So we can simplify this further by canceling this Rs plus RL from top and bottom. So we're left with a cubic instead of quartic. And now the derivative expression looks like so. So we have in the numerator Rs minus RL over Rs plus RL to the third times Vs squared equals 0, which will give us the optimal Rs value. So thus, this expression equals 0, so we set the numerator equal to 0. So the optimal load resistance is equal to the source resistance in order to maximize the power PL delivered to the load. So we found here the values we should choose for the reactance of the load and the resistance of the load to deliver maximum power to the load. So we can express our optimal load impedance as RL plus JXL, substituting the values we found. So Rs minus JXS. And this is the optimal that we found. And you can see that this exactly equals the complex conjugate of the source impedance. So therefore, this is what the maximum power transfer tells us, that if we have a fixed source impedance and we want to choose the values of the load impedance, we should choose the load impedance to be the complex conjugate of the source impedance so that we deliver maximum power to this load. And if we substitute this expression of ZL into the circuit, then we'll see that the total impedance, which we know is equal to ZL plus ZS, where here we're using ZS star as the optimal complex conjugate of the source impedance as our optimal value. Then we're left with 2 times the source resistance as our total impedance in the path. So then we have that the current is equal to Vs over 2Rs, and thus we have the maximum power delivered is equal to I squared RL is equal to Vs over 2Rs squared times RL, which is just equal to Rs. So then we get the maximum power is equal to Vs squared, the 4, which is 2 squared, comes out in the bottom, and then the Rs squared on the bottom cancels with the Rs in the numerator. So we get this expression as our maximum power delivered to the load. So overall, this is the derivation of the maximum power transfer theorem. Now, one thing to keep in mind is that in this model, we had a fixed source impedance. So in this problem, we had assumed we to begin with, we have a fixed value for Rs and Xs. But what if we consider the problem where instead of a fixed source impedance, we have a fixed load impedance? So this case will be a little bit different. So in this case, instead of an unknown load impedance to start with, we have this as fixed. And the question still remains, we want to deliver the maximum power to this load. Now, what should we choose for the source impedance? So you can see we swapped the question around. So in this case, we should choose, since we're free to choose the source impedance now, the best choice is if we choose the source resistance equals 0 and the source reactance equals the negative of the load reactance. So basically, we would have this load reactance canceling out, the source reactance canceling out with this load reactance, and we would set this to 0 so that there is no internal source resistance wasting voltage. So in this case, we would get an equivalent circuit that's just a voltage source Vs driving a resistor RL. So you can see in this case, the maximum power delivered to the load will be PL equals, so we have Vs over RL squared as the current magnitude squared times the load resistance RL. And this gives us Vs squared over RL as the power delivered to this load resistor. So you can see the conditions of the problem matters, because in the extreme case, let's consider if we choose the load resistance, to approach 0, what happens? Then the load power can actually approach infinite. This is because we have a voltage source, which we assume has no current limits on it. It's just the ideal sinusoidally varying voltage source. And we have a very, very small resistor. In that case, we can essentially deliver a huge amount of power, approaching infinite, to this small resistor. And that would give us almost infinite power that's delivered to the load. So overall, this is an analysis of the maximum power transfer theorem. And this work just shows how the problem changes if instead we consider a fixed load impedance and where we're free to choose the source impedance. Now, in the maximum power transfer theorem, it's not that way. The condition of this theorem states that the source impedance is fixed and we're maximizing the power delivered to the load by choosing the load impedance. So in impedance matching, the problem is usually the case where we have this fixed source impedance and we want to design a matching network such that the load impedance is the complex conjugate of this source impedance, allowing us to deliver maximum power to a load. So I hope you found this video helpful. And if you did, please give this video a like and subscribe to the channel for more videos like this in the future. Thank you.